So this video is about the Newsvendor model. The Newsvendor model is another inventory model that determines the order quantity, that is, how many should I order in this scenario. So you have to determine how many I need to order prior to the selling period. And we do this when demand is uncertain, therefore we can only maximize an expected value. And this is more difficult because there are overage and underage costs. And we'll get to all of these red highlighted words in much more detail. But I think one of the best ways to think about this problem is to think about this video.
The TV isn't the best place for news, so the news voice where I go. Here's my friends complaining about paper demand being high and low. Every day and day the market trends are changing, and trust me, there's no way to know. Look at the history, but it's a mystery. And then we start to think, saying like, friend, you know I want some dough. This operation is too tricky for me. Come on now, plan it for me. I'm going crazy, please help me, news boy. Let's not talk too much. Grab those numbers and leave the planning to me. Order now, follow my lead. Come on, order now, follow my lead. Newsvendor Model's here for you. If your item stock's too low, dissatisfied customers now grow. You'll be losing your clients, but if your stock's now overflow, not all of them will end up sold. Any excess you will have to throw. The demand's fluctuating low, high, low, high, low, high, low, high. The demand's fluctuating low, high, low, high, low, high, low, high. The demand's fluctuating low, high, low, high, low, high, low, high. The demand's fluctuating. Operation management is here to save you. Newsvendor Model's here for you.
So that is the Newsvendor model. And so what did we hear there? We heard that demand was fluctuating, so demand is uncertain. And there was also these overage and underage costs, which we'll get to in more detail. And so what does it happen and why is it called the Newsvendor problem? The reason it's called the Newsvendor problem is this is the problem faced by a news vendor. So at the start of each day, a news vendor must first decide on how many papers to purchase. That's the order quantity. And they must do that before the selling period. So they show up at the printer, they say, today I want 50 papers to sell on the streets. And they can only place one order. They can do it in the morning, and if they either sell them or they don't, they have one opportunity to place an order. It happens before the selling period. Then they go to their corner and they start selling newspapers, and daily sales cannot be predicted exactly. So you have some estimate, you have some forecast, but the demand for today's newspaper is a random variable. So that means demand is stochastic. We can characterize what that demand is based on a probability distribution. We don't know exactly how many newspapers will be sold today. And so what makes that difficult is at the end of the selling period, if we have any newspapers left, no one wants an old newspaper, or they want tomorrow's newspaper tomorrow. And so what happens is you can maybe either just have to throw them away, and so whatever you invested in your newspapers are lost, or they have a reduced value. So maybe your supplier will buy back old newspapers, recycle the paper, but not for as much as you paid for it. And so that's where this overage and underage costs come in, is that we want to sell as many newspapers as possible. If I don't have a newspaper, I can't sell it. However, if we have too many newspapers left over, there's a cost to that as well. And therefore, we need to balance these overage and underage costs. So that is something you likely have seen in other examples. So I'd like you to think about, where do you have the situation where you need to determine how many to buy before the things you want to have sell happen, and at the end, there's overage and underage costs. So hopefully you've thought of a few. One really good example of this is if you've ever gone shopping the day after Halloween for Halloween candy, or the day after Valentine's Day for Valentine's Day candy. That is exactly the Newsvendor process. And so what a retail store needs to figure out is before the holiday, they need to order seasonal products. They have one opportunity kind of beforehand because it takes time for them to get their products, and they have to determine how many Easter bunnies, how many Cupid do you need? And then if they don't have enough, then they don't make sales and they don't make any profit. But if they have too many, if you've ever shopped for candy the day after a holiday, what do? They mark it down. And so they've marked this down. And so there is some value at the end of the selling period, but it's definitely reduced. So that is an example of where this comes from. There are many, many others. This also occurs when people think about overbooking. So if you've ever been on a plane and you've heard this statement, we want to overbook, there are overage and underage costs associated with that. We'll study that later in upcoming lecture. You also could think about this in your daily life. If you need to figure out how long should I go to, for example, go to the airport before your flight. If you leave too early, then you waste time, and being at the airport, you could have been doing something else. You had to get up early, that's a cost. But if you leave too late and you miss your plane, that also has costs. And so there's expected time it takes from you to get from your door to the airport gate, but that's random, and you have to make this decision before you know exactly what that will be. And so there's honestly lots of examples of the Newsvendor process. I think thinking about it as a newspaper is actually quite helpful when we think about the math in this problem. All right, so as a reminder, the decision variable, what we get to decide, is Q, which is the number of units to purchase before demand materializes. And an input is the demand, so the number of units demanded. We'd love to know that exactly. Unfortunately, this is a random variable, and so we can estimate it. We might have a mean and a standard deviation. We know its distribution, but we don't know exactly what's going to happen every day, okay? And so what is the challenge associated with the Newsvendor problem is we basically have a Goldilocks scenario. So just as a reminder, Q again is the number to order, that's our decision variable. D is a random variable, so we don't get to control D. And you can think about there being three cases, just like in Goldilocks. Case one is that D is too big. So in other words, you had more demand than the number of newspapers you bought that day. What is the dilemma there? Well, the dilemma there is we have too little supply or we have too much demand. And so there exist customers that couldn't have their demand be fulfilled. And this is what we call as underage or shortage costs. So we'll call this C of U or C of S. So we're short some newspapers. And so we don't get to make that sale, which is a loss of profit. So that's not a great situation. But so you could say, well, then to prevent that, what if I just make Q really big? That's great for sales, but that has a cost to it as well. And that means demand would be too small. So if you make Q too big and Q is less, or Q is more than D, then you have too much supply. And so we fulfill all the demand that day. We sell everybody a newspaper that wants one, which is great, but has a consequence. And that consequence is you have leftover newspapers. And those leftover newspapers have a value that is reduced. And so thinking about newspapers, no one wants an old newspaper. Thinking about seasonal products at the end of the season, after Halloween happens, you have to reduce or mark down those things, and that costs you. And so when demand D is less than Q, that's what we call as overage cost. We had over or too much inventory, and that cost us something. Now, just like Goldilocks, we would love it to be just right. Our ideal situation is that demand is exactly equal to the supply that we have, which is what we would love. The problem here and the challenge here is we only can control Q. So we can control how many, but we can't control the demand. So the demand is stochastic. We have an estimate for it, but it's a random variable. So we'd love for D to always be equal to Q, but over time, some days D will be bigger than Q, sometimes D will be less than Q, and sometimes D will be equal to Q. And that's what we're really striving for, but we need to look at this in an expected value perspective because we can't control the outcome of D. And so if you want to look at the Newsvendor problem a little more formally, We have demand that's uncertain. So we have this problem, and the Newsvendor problem is only applicable if we have this trade-off between stocking too much, then we have excess inventory. Stocking too little, we lose profit or lose that sale. So we have this overage and underage cost that is going back and forth. In terms of some assumptions, we will learn about the basic Newsvendor problem. There are many, many extensions of this problem in academic literature and implementations in practice. The problem we're going to look at assumes there's a single period. So we are figuring out Q once, and then there's a selling period, and then we may redo this again, but we're only considering a single opportunity to buy Q and a single selling period. Again, demand is random. So D is a random variable, but we know its distribution. So we'll know its cumulative distribution function, and that will help us set Q. Again, we have overage and underage costs, but one of the assumptions we're making is that there's linear overage and underage costs. What that means is if I'm under by 1 unit, or if I'm under by 2 units, there's a linear cost to that. So there's a per unit cost of being over by 1, 2 would be twice as much, 3 would be 3 times as much, and so forth. And so that's an assumption you make to set Q star that may or may not fit depending on your application. And then the goal is that we're trying to minimize an expected cost or maximize an expected reward. And the key thing here is expected, because we want to maximize on average or an expectation of what will happen, but we can't control each outcome. So sometimes during a selling period will be too much, sometimes will be too little, but we're trying to maximize an expected value. All right, so in terms of the notation, we have input parameters. So again, we need to know, here I'm going to use X, the demand in units, which again is a random variable. G of X is the cumulative distribution function of demand. So the Newsvendor model is an extremely versatile model. It works for any distribution function. We just need to know it. And so we'll do some examples with normal demand, but it's not the only thing you need. And remember, there's a relationship between the cumulative distribution function of demand and the probability density function of demand. If they're continuous, this is the, we would take the derivative to get from one to the other. And then we also need to know the overage cost in dollars per unit, and the key here is per unit, left over after demand is realized, and then the underage or C of U, or sometimes C of S, is the underage or shortage cost per unit of shortage. So these are both per units, and they should be in the same units. Here, I'll just give them in dollars. And then what do we determine? We determine Q star, and that's the production or the order quantity and number of units. One thing to note, if you're looking at the book, this is O star, but O is weird because it looks like 0, so I converted it to Q. All right, so how do we determine Q star? Similar to what we did in the EOQ model, we need to think about a cost function, and we want to minimize that cost function. And so in this case, we can think about our cost as expected overage cost and expected underage cost. And so if you think about, remember our information in terms of input parameters, CO is per unit over, and CS is per unit under or short. And so those are a constant or an input parameter. And so what we need to figure out is then how many units will we have over and how many units will we have under. But again, this will change because we don't know the demand. The demand is a distribution. And so if we think back to a probability and statistics class of the definition of the expected value, if we have a continuous distribution, this maybe reminds you of what's going on in terms of expected value. What's going on here? Well, if we're over, that means we have more Q than X. And so why is it max 0 is because we don't want a negative number. So we only get an overage cost if Q is bigger than X. If Q is less than X, we would say there's no overage cost, and that would be 0. On the shortage or underage cost, that happens when X, the demand, is bigger than Q. And remember, these CO and CS are per unit. And so then this is the expected value equation for that. And so if you think about that, remember G of X is the demand distribution, the probability mass function. And so if we then simplify here, we get this second equation. And so how do we figure out the minimum? We need to take the derivative. We're trying to find Q. Where's Q star the minimum of this function? So we take the derivative of y of Q with respect to Q, and then set the derivative equal to 0 and solve for Q star. So if we do that, we can also check the second derivative. And so because that's greater than 0, we know that it's convex. And so it will occur at this minimum point. And so if we do that, we take the first derivative with respect to Q and set it equal to 0, we get this last equation on this slide. So one thing to note is we have a function that's a function of the cost of overage and times the cumulative distribution function of G of Q star, and then minus the cost of shortage times 1 minus G of Q star equals to 0. So continuing this derivation, that equation, we can move things around. So we can move things from left to right. And what do we get? We get this equation here. And so one thing to note is, just as a reminder, what is the cumulative distribution function? Well, it's the distribution function that demand is less than or equal to Q, which is G of Q. And what is the probability that Q is greater than D? Remember the relationship, that's 1 minus the cumulative distribution function, that it's less than D. And so if we have this equation, we now need to solve for Q. And so how do we solve for Q? Is we just rearrange things, do some algebra, and we get this equation where G of Q star is equal to CU over CO plus CU. And that is called the critical ratio. And so the idea is we want to find Q such that the probability we satisfy all demand, the demand is Q or lower, is equal to the critical ratio. And so what we will do, what's kind of cool about this is, even though all this derivation, is we just need to calculate this critical ratio. And once we have this critical ratio, we just need to find Q such that it is at least as much, the cumulative distribution function of Q star is at least the critical ratio, and that's how optimally we should set Q star. And we'll do some examples to illustrate that. All right, so what's going on in terms of this? If you want to think about this and break this up, the critical ratio balances the risks and benefits of ordering a unit. So if you think about ordering one more unit, so I say, okay, I'm going to order one more unit, that will increase my chance of overage. So the idea that we have too much inventory left over. And so you could think about what is the expected loss on that Qth unit, that's CO times the cumulative distribution function, right? And just a reminder, that's the probability demand is less than or equal to Q. And so if I order one more, that increases the chance of overage. Okay, hopefully intuitively that makes sense. However, if you think about the benefit of ordering one more unit, that hurts us in terms of overage, but it helps us in terms of fulfilling demand. And so we also have a smaller chance of not meeting all of our demand. And so what's going on with this Newsvendor model is a balance of these two things. And so if you see on this graph, as more units are ordered, the expected benefit from ordering one unit decreases, while the expected loss of ordering one unit increases, and the critical value balances these two things so that we can set Q where it's the minimum expected costs associated with overage and underage. All right, so to hopefully just give you some kind of background and say, okay, am I understanding this? My kind of knowledge question to you would be, what would the critical factor be if the cost of understocking is a really big number? So if C of U is really, really large. So if I didn't have enough inventory and that cost me a lot, what would happen in terms of our critical factor. So if you need some time to pause, please do so. So hopefully you have reasoned that the correct answer here is B, or 1. So if you think about CU being a really big number, let's say CU is 1 billion and CO is just like 10. So 1 billion divided by 10 plus 1 billion, it approaches 1, okay? So what does that mean? That means we need to set Q star such that we fulfill the 100% of the cumulative distribution function. So we would need to basically say we never want to stock out. We never want to not have enough. You may say, okay, when would that actually happen? Well, in critical systems, say you work at NASA and you need to make sure you have all the things needed for a launch. Oftentimes the understocking, or not having enough, is really high compared to having one extra. And so in some critical, safety critical situations, CU is much bigger than CO. And so what does the critical factor tell us? It tells us, make sure you have enough of whatever that is, that you meet all expected demand. The biggest expected demand that could happen, you should have enough to cover that. All right, so we've done all this stuff, great, but how do I actually determine Q star? All right, so the steps to determining Q star. First, we need to know what the demand model is for the selling period. That is, we either need to be given or we need to look at historical data to figure out a cumulative distribution function. We're going to call that big G of Q. And that would reflect the possible demand outcomes. This could be a discrete probability distribution function, normal, Poisson, whatever. It works on any distribution function, but we need to know that and we need to characterize that. And so just as a reminder, we would need to know or be given the cumulative distribution function of demand. That's step 1. Step 2 is we need to gather economic inputs and calculate the critical value. And so typically the inputs would be things like selling price, production or procurement costs, salvage values of inventory, and those would allow us to calculate C of U, the cost of underage, as well as the cost of overage. And we'll do some examples of how to do that. So if it's price and selling, there's this nice relationship. I want to encourage you, though, to not get just stuck in selling price procurement. This is actually a very versatile model that can work for things that aren't just selling price and production price. So you need to calculate the critical value. This will be a value always between 0 and 1. And then what we need to do is we need to choose Q star, which again is the quantity to order that maximizes the expected profit or minimize expected cost. And that is done as long as we select Q star such that the cumulative distribution function is greater than or equal to the critical value. So as long as we set Q star using the critical value, we will always be maximizing whatever our cost function is, either maximizing expected profit or minimizing expected cost. So that works for any distribution. One thing to note is that if our demand distribution is normally distributed, we have some nice special equations. And so what we have here is if we have normal demand, what we can do is if we have normal demand, we're given the mean and the standard deviation of that distribution during the selling period. We need to then calculate our critical factor, and so we'll get some value between 0 and 1. Then we need to go look that up in the normal table or use Excel function norm inverse, and then round up if necessary, and that will give us Z, and then we can plug that all in to get Q. So again, I want to emphasize anything with Z only works if you have normal demand. So it's a special case because the Z tables give us the cumulative distribution function with these relationships. The Newsvendor problem works with any cumulative distribution function, but you cannot be using this equation. And so let's just do a simple example to get you used to these equations, and then we'll do some more examples in some more videos. So in a simple example where we have that demand is normally distributed with average demand mu of 120 papers per day and standard deviation of 15 papers. As a news vendor, we buy papers for 70 cents. So that's what we pay our supplier, but we sell them to people, to customers, for $1.25, which is great. But then any extra newspapers left at the end of the day, the supplier will buy back, but only will give us 30 cents per old newspaper. So if we think about step one, we know our demand distribution. So per day is normally distributed the mean of 120 and a standard deviation of 15. Second, we need to calculate our critical value. So our critical value here, we first need the cost of underage and the cost of overage. And so if I'm under one paper, what does that mean? It means I won't be able to make a sale. And therefore, I lose out on the opportunity to make 55 cents in profit. So for every paper that I don't have when someone wants it, it costs me 55 cents per paper not there. In terms of overage, overage means I have too much inventory. If I have too much inventory, at the end of the day, I have papers left over. If I have one paper left over, how much does that cost me? And so that one paper left over cost me 40 cents because I invested 70 cents to my supplier. At the end of the day of a leftover newspaper, the supplier gives me 30 cents, but I'm losing 40 cents per paper that I have left over at the end of the day. So that's the C of O. So then once you calculate those, we need to calculate the critical value, which here is 55 cents divided by 55 cents plus 40 cents. If you do the math, that gives you a critical value of 0.578. So that's step two. And then step three is to calculate Q. So how do we calculate Q? Well, because we have normal demand, we can use the Z value. And so we basically want to figure out graphically what is the value where the area under the curve, the blue area under the curve, is 57.8% when we have a mean of 120 and a standard deviation of 15. So that's what we can go look up the Z value for 0.578, and that gives us a Z value of approximately 0.2. And we can then use the equation Q plus Z times the standard deviation, which if we plug in for this specific normal demand gives us that we should go and buy 123 papers in the morning and hope that we sell all of them. And sometimes we'll have more, sometimes we'll have less, but this is the value that maximizes the expected profit or minimizes the expected cost for this example.